something is happening in physics that should not be happening at all. A signal has been detected that does not fit into any known rule of the universe. It does not behave like anything predicted by modern science. It does not match what our equations say should be possible. And yet it exists in real data measured by advanced instruments designed to eliminate mistakes. This is not a small, irregular reading. This is not a minor error in calculation. This is something that appears again and again under careful analysis. It refuses to disappear even when scientists try to remove every possible source of noise or distortion. Even leading physicists, including Brian Greene, are treating this seriously. Not because they want to overturn physics, but because the data is forcing attention. When people who study the deepest laws of reality start saying that something does not fit, it means the foundation itself is being tested. Modern physics is built on two main pillars. One is general relativity, which explains gravity, stars, galaxies, and the structure of the cosmos. The other is quantum mechanics, which explains particles, atoms, and the smallest building blocks of reality. Together, these two theories describe almost everything we can observe in the universe. And for a long time, they have worked extremely well. They have predicted planets, black holes, light behavior, and even the expansion of the universe with incredible accuracy. Many scientists believed that physics was getting close to a complete understanding of reality. But now, something has appeared that does not follow either of these pillars. The anomaly shows behavior that should not be possible under current models. It appears in precise measurements that were designed specifically to test the limits of physics. At first, researchers thought it was a malfunction. Instruments can fail. Data can be corrupted. Background noise can create false signals. That is always the first assumption in science. So they checked everything. They recalibrated the equipment. They repeated the experiments. They compared results across different systems. They removed known sources of interference. They tested alternative explanations. And still, the anomaly remained. It did not weaken. It did not disappear. It stayed consistent. This is where things become more serious. In science, most strange results fade away under deeper testing. Very few survive repeated verification. But this one continues to appear under controlled conditions. It behaves as if it is part of reality itself, not an error inside the measurement. The most disturbing part is that it does not just challenge one small idea in physics. It challenges the structure that connects many ideas together. If this result is correct, then one or more assumptions at the foundation of modern physics may be incomplete or wrong. That is why this discovery is getting attention from researchers around the world. Because even a small crack in fundamental physics can lead to major changes in how we understand everything from atoms to galaxies. Right now, there is no final answer. Scientists are still analyzing the data. Some believe it could be an unknown particle or force. Others believe it may reveal physics that we have never seen before. And some believe it could expose limits in our current understanding of the universe itself. But all agree on one thing. This is not something to ignore. Because if this anomaly is confirmed, it could mean that our current model of the universe is not complete. It could mean that everything we think we understand about space, time, and matter is only part of a much larger picture that we have not fully uncovered yet. And that is why this discovery matters. In this video, we will break down exactly what scientists detected, why it breaks known physics, and what it could mean for the future of science. We will also look at the most serious explanations being considered right now and why none of them are fully satisfying yet. Stay with this video until the end because what you are about to see could change the way reality itself is understood. And if you enjoy deep science stories that explore the edge of human knowledge, subscribe to this channel. There is much more coming, and some of it goes even deeper into the mysteries that physics has not solved yet. The first reports of the anomaly did not sound dramatic at all. In fact, they looked like a small inconsistency buried inside a massive amount of data. A single point that did not line up with predictions. In modern physics, this happens often. Instruments collect huge amounts of information every second. Most of it is filtered, corrected, and matched against known models. Tiny errors are expected. Random noise is normal. That is why scientists are trained to ignore early surprises. But this was different. The signal came from a highly precise measurement system designed to test extremely sensitive physical behavior. In this kind of setup, even the smallest deviation matters. The equipment is built to eliminate almost every known source of error. Temperature changes are controlled. Magnetic interference is blocked. Background radiation is measured and removed, yet something remained. A pattern appeared that did not match any known prediction from current physics models. It was not slightly off. It was clearly outside the expected range. The deviation was measurable, consistent, and repeatable under the same conditions. At first, researchers assumed it must be an error. That is the standard response in science. Instruments can drift. Calibration can fail. Software can misread inputs. Even cosmic rays from space can sometimes interfere with detectors and create false signals. So the team checked everything. They reran the data processing steps. They tested different filters. They compared raw results with cleaned results. They even cross-checked with independent systems designed to verify accuracy. In many cases like this, the anomaly disappears once corrections are applied. But this time, it did not go away. The same pattern showed up again and again. It appeared in separate runs of the experiment under slightly different conditions and even after adjustments meant to eliminate possible sources of error. This is one of the key reasons scientists began to pay closer attention. Random noise does not behave like this. It does not survive repeated testing in controlled environments. The anomaly also showed a very specific structure. It was not chaotic. It followed a pattern that suggested something physical was producing it. That is important because in physics, structure usually means cause. Random noise has no consistency. Physical processes do. Some researchers compared it to known effects and found no match. It did not behave like particle interactions predicted by standard model of particle physics. It did not align with expected results from gravitational or electromagnetic models either. This is where the situation became more serious, because when a result does not match multiple independent frameworks at the same time, it suggests a deeper issue. Not just a missing detail, but a possible gap in understanding. Still, the scientific process demands caution. Many past anomalies have disappeared after further analysis. Some were traced to overlooked calibration errors. Others came from rare environmental interference that was not properly accounted for at first. So the early reaction remained skeptical. Teams across different institutions began rechecking the data. They looked for alternative explanations. They questioned every step of the measurement process. Some even tried to reproduce the effect using different equipment entirely. And yet the anomaly continued to appear. If this signal is real, then it should not exist at all under the rules of modern physics. That is the part that makes it so unsettling. Every known framework in physics has strict limits. These limits are not flexible. They are built from decades of experiments that agree with each other with extreme precision. When something breaks those limits, it is not treated as a curiosity. It is treated as a potential crisis for the model itself. The first conflict comes from the standard model of particle physics. This model describes how particles behave, how forces interact, and how matter is built at the smallest level. It has passed thousands of experimental tests. It predicts results with astonishing accuracy. But the anomaly does not follow those predictions. It shows behavior that does not match any known particle interaction. In some interpretations, it may suggest energy levels that should not be possible under current rules. In others, it may point to a process that violates expected conservation patterns. In simple terms, something is happening that the standard model does not allow. The second conflict comes from general relativity. This theory explains gravity as the bending of space and time. It works extremely well for planets, stars, and galaxies. It also explains black holes and the expansion of the universe, but the anomaly seems to sit in a space where relativity and quantum rules overlap. That is already a known problem area in physics. The two theories do not fully agree at extreme scales. Still, no confirmed experiment has ever directly broken both at once. This result appears to push into that boundary. Some versions of the data suggest effects that seem too fast to fit normal interaction times. Others suggest shifts that look like symmetry breaking, where expected balance in physical behavior is not maintained. In physics, symmetry is not just a pattern. It is a deep rule that helps define how forces and particles behave. When symmetry breaks unexpectedly, it can signal new physics. That is why this situation is so sensitive. Physics depends on consistency. Every law connects to another law. Gravity links to motion. Motion links to energy. Energy links to matter. If one piece fails, the rest can become unstable. It is like a chain where every link supports the next. A single confirmed contradiction is enough to force a full review of how the system is built. History shows this clearly. There have been moments when small anomalies changed everything. Tiny errors in planetary motion led to the discovery of new planets. Unexpected results in atomic experiments led to quantum theory. Even small deviations in light behavior helped reveal that space and time are not fixed. Each time, the pattern was the same. At first, the result looked wrong. Then it refused to disappear. Now, this new anomaly is entering that same category of concern. Not because it is already proven to be new physics, but because it refuses to behave like anything expected under known rules. And that is where the real tension begins to build. The first response from the scientific community was simple. It must be a mistake. That is always the safest assumption when something does not fit known physics. Measurement error is the most common explanation. Even the most advanced instruments are not perfect. Small fluctuations in temperature, hidden electronic noise, or unexpected cosmic radiation can sometimes distort results. There are even rare cases where data storage systems introduce subtle corruption that is almost impossible to detect at first. So researchers went back to the beginning. They checked every layer of the experiment. They reviewed calibration logs. They tested background conditions. They even simulated possible interference scenarios to see if the same pattern could appear by accident, but the anomaly still held. That forced a second explanation. Maybe it is not an error. Maybe it is something real, but unknown. This is where the possibility of a new particle or force enters the discussion. Physics has a history of discovering hidden components of reality. Neutrinos were once considered nearly impossible to detect, yet they are now a confirmed part of nature. Dark matter is still not directly observed, but its effects are seen across galaxies. So some scientists began asking if this anomaly could be pointing to a new force or particle that has never been measured before, something that interacts so weakly with known matter that it has stayed hidden until now. But this idea brings its own problems. Any new particle or force must still obey conservation laws and fit within a larger framework. It cannot simply exist in isolation. It must connect to everything else we already know. So far, no version of this explanation fits the data cleanly without creating contradictions elsewhere. Then there are more extreme possibilities. Some theoretical models, especially those linked to string theory, suggest that reality may have extra dimensions beyond the three spatial ones we experience. In these models, particles and forces are different vibrations of tiny strings existing in a higher dimensional space. If extra dimensions influence physical behavior, they could potentially distort measurements in subtle ways. That could, in theory, create anomalies like the one being observed. However, there is a major issue. These ideas are extremely difficult to test. There is no direct experimental evidence of extra dimensions, and no confirmed mechanism that connects them to the kind of signal being seen in this case. Finally, there is a more uncomfortable possibility. The problem may not be something new in nature. It may be something missing in our understanding, a limitation in current models. This means the equations themselves might not fully describe reality at certain scales or conditions. Physics has faced this before. Newtonian mechanics worked perfectly until it did not. Classical theories of light worked until they failed under precise testing. Each time, the problem was not nature changing, but understanding expanding. But accepting this explanation opens another challenge. If the models are incomplete, then there may be more unknown gaps hidden inside other well-tested results. That would mean the foundation of current physics is more fragile than expected. Each explanation, whether simple or extreme, seems to solve part of the problem, but none of them resolve everything without creating new conflicts. At this stage, the discussion changes direction. It is no longer only about errors or unknown interference. Some physicists are now considering a more serious possibility. The anomaly may be pointing toward physics that has never been seen before. Physics has a history of expanding when old limits fail. When enough strange results appear in the same place, they can signal that the current framework is not the full story. That is why some researchers are now asking whether this could be evidence of physics beyond the standard model of particle physics. The standard model is one of the most successful theories ever created. It explains nearly every known particle and force except gravity. It has survived decades of testing with extreme precision. But it is also known to be incomplete. It does not include dark matter. It does not explain dark energy. It does not fully connect with gravity. Now the anomaly raises a new question. Could this be one of the first real signs of that missing layer? If so, the implications are large. One possibility is that the anomaly is connected to a new set of rules that extend or replace parts of current physics. This would not be a small update. It would be a restructuring of how fundamental laws are understood. There is also the long-standing problem in physics, connecting quantum mechanics with gravity. The laws that describe the very small do not match the laws that describe the very large. For decades, scientists have tried to bridge this gap without success. But some researchers believe unusual signals like this could be hints of that connection forming in unexpected ways. If gravity and quantum behavior are interacting in a new way, even in a small region or under rare conditions, it could produce effects that look like contradictions in data. That would mean the anomaly is not random. It would be a clue. There is also a deeper implication. Some theories suggest that phenomena like dark matter and dark energy are not separate substances, but effects of unknown physics acting across space. These effects have never been directly observed, but their influence is seen in galaxies and cosmic expansion. A signal that does not fit existing rules could potentially be linked to these unknown components. It could represent a small window into processes that shape the universe on the largest scales. What makes this even more striking is the possibility that reality itself may not be as simple as current models suggest. Most people think of physics as a finished system of laws, but modern research increasingly shows gaps, tensions, and unresolved problems at the edges. Some physicists now describe this situation carefully. They do not claim discovery. They describe pressure points in the model, places where new physics could emerge if enough evidence accumulates. The anomaly sits directly in one of those pressure points. And if it continues to hold under further testing, it may suggest that the universe is operating with layers of structure that have not yet been mapped. When results like this appear, the first reaction is never celebration. It is caution. That is the standard in physics. Strange data does not become discovery until it survives intense testing from multiple independent groups. Till then, it remains a question mark. Brian Greene has spoken about this kind of situation many times. His view is clear. The history of physics shows a repeating pattern. Major breakthroughs rarely come from expected results. They often come from small contradictions that refuse to disappear. In the early stages, these contradictions look like errors. Most of them are but a very small number survive every attempt to explain them away. Those rare cases are where science changes direction. This is why anomalies matter. They are not accepted as truth. They are treated as pressure points, areas where current understanding might be incomplete. In this case, the reaction from the scientific community has been careful but alert. No one is claiming a discovery. That is important. In physics, a single result is never enough. A result must be reproduced, tested, and confirmed under different conditions before it can be trusted. This is where the process becomes global. Research teams in different countries are now repeating similar experiments. Independent laboratories are running their own versions of the tests. Some are using more sensitive equipment. Others are changing environmental conditions to rule out hidden interference. The goal is simple: see if the same anomaly appears again. At the same time, data analysts are going through the original results line by line. In modern physics, raw data is often reprocessed in many ways. Different algorithms can reveal hidden patterns or expose mistakes. Even small differences in processing can change interpretations. One lesser known fact is that in high precision physics, researchers often keep blind analysis protocols. This means they hide key parts of the data during initial review to prevent bias. Only after all checks are complete do they reveal the full results. This helps avoid seeing patterns that are not really there. That is how seriously this process is taken. Even with all this caution, interest remains high. Not because the anomaly is confirmed, but because it resists easy explanation. Most false signals disappear quickly under scrutiny. This one does not. Still, there is no official claim of new physics. No paper has declared a breakthrough. No theory has been rewritten. The scientific community is holding back judgment until full verification is complete. That is the tension. On one side, there is a result that does not fit known rules. On the other side, there is a system designed specifically to eliminate false conclusions. Between those two sides, the investigation continues. And every new test brings the same question back into focus. The next stage is already in motion. When a result refuses to disappear, physics does not stop at discussion. It moves to verification. Everything now depends on whether this anomaly can survive under stricter conditions. The first step is repetition. More experiments are being designed to recreate the same conditions with even tighter controls. Small details that were previously considered insignificant are now being treated as critical. Temperature stability, electromagnetic shielding, timing accuracy, and even vibration levels are being reduced to near theoretical limits. In many advanced laboratories, instruments are being recalibrated specifically for this investigation. Some setups are being rebuilt from scratch to eliminate any hidden bias in the original design. At the same time, completely independent teams are joining in. This is one of the most important parts of modern physics. A result is never trusted if it only appears in one place. It must be seen again under different conditions by different researchers who have no connection to the original experiment. That process is already spreading across research centers around the world. New instruments are also being brought into the search. Some of these devices have higher sensitivity than anything used before. They can detect smaller fluctuations, weaker signals, and more subtle interactions than earlier generations of technology. A lesser-known detail in experimental physics is that many breakthroughs happen not because nature changes, but because measurement tools improve. Something invisible yesterday can become visible today simply because detection power increases. That possibility is now part of the investigation. There is also global collaboration forming around the anomaly. Data is being shared across institutions. Independent teams are comparing results using different methods of analysis. Even small differences in interpretation are being carefully documented to avoid bias. In some cases, raw data is being re-examined using completely new computational models. These models are designed to test whether the anomaly could emerge from hidden patterns that were previously overlooked. Everything is focused on one question. Is the effect real, or is it an artifact of measurement? The answer will decide the direction of this entire discussion. If the anomaly is confirmed across multiple independent experiments, the implications would be serious. It would mean that current physics models are missing a piece of reality. In that case, textbooks would not just be updated. Entire sections of theoretical physics would need revision. Some equations that are currently considered complete might turn out to be approximations of a deeper system. But there is another possibility. If the anomaly disappears under improved testing, it will still have value. Negative results are not failures in science. They are corrections. They refine methods, improve precision, and prevent future errors. Even a false anomaly can lead to better instruments and stronger experimental design. Either outcome pushes science forward, and that is why this moment is important. Not because a discovery is guaranteed, but because the investigation itself is revealing how carefully reality must be tested before it is understood. This anomaly sits in a very strange place in modern science. It is not confirmed as a discovery. It is not confirmed as an error. It exists in between, waiting for more proof. That is exactly what makes it so important. If it turns out to be a mistake, it will still have value. It will improve how scientists build experiments and how they check data. It will make future research more precise. Science often moves forward by removing false signals and refining methods. But if it is real, the situation changes completely. A confirmed anomaly that breaks current expectations would mean that something deep in our understanding of the universe is incomplete. Not slightly wrong. Incomplete. That difference matters. It means there are rules or layers of reality that have not yet been discovered. History shows that this is how physics evolves. Small inconsistencies once led to major revolutions in science. Results that were first rejected later became the foundation of entirely new theories. Every major shift in physics started with something that did not fit. This is why scientists are not rushing to conclusions. They are watching carefully, testing everything, doubting everything. Because in science, certainty only comes after repetition, not surprise. Right now, this anomaly is still under investigation. It sits at the edge of knowledge, where known laws stop and uncertainty begins. That is often where the most important discoveries are hiding. The universe has always been more complex than it first appears. Every time humans think the rules are complete, new layers emerge, new forces, new particles, new behaviors that were invisible before. So the real question is not just what this anomaly is. The real question is whether it is a glimpse of something new or just a reminder that even our best understanding of reality still has gaps. Either way, the search continues, and the next results could change everything again. If you enjoyed this journey into the edge of modern physics, do not forget to like the video and subscribe to the channel for more deep science stories like this. There are still many mysteries waiting to be explored, and some of them may be closer to rewriting reality than anyone expects.